This video is going to cover our Lesson 8 practice problems. We're assigning number 1, A through D only, and number 6. So I went ahead and crossed off E and F. We're going to skip those two. For an experiment, a scientist designs a can that is 20 centimeters tall and holds water. A tube is installed at the bottom of the can to help it drain out. At the beginning of the experiment, the can is full, but every minute after the start of the experiment, 2/3 of the water is drained out. So, we need to explain why the height of the water in the can is a function of time. So height of the water is a function of time. That's telling us again that we have an input here of time and an output of the height of the water. And just a reminder about how functions work, that no matter what, if we have a certain input, we can only have one output at a time. So at any given time, there is only one height of water in the can. Now that makes sense because if I give it a certain snapshot, there's no way that this can is going to have two levels of water at exactly the same time. So that is our idea, that for each input, which in this case is time, there is only one output, and that is height of water. So we can't ever have two heights at the exact same time. So the height centimeters is a function of f of time t in minutes. Height is a function f of time t in minutes since the beginning of the experiment. It wants us to write an expression for the height of the can, an expression for f of t. So our function f of t is the height of the can for a certain amount of time. So the way we need to think about it, we've been writing it in with our starting value times the amount that it keeps, and however many times we are going to be doing that cycle. So this can starts with 20 centimeters of height in the can. So I'm going to start with my 20. If it loses 2/3, remember we want to think about how much it keeps. So if it loses 2/3, that means it keeps 1/3 of its water every single t minute that this experiment runs. So there's our equation. And now we're going to use that equation to calculate and record the values when t is 0, when it's 1, 2, and 3. So let's start that out. When t is 0, that's our starting amount of how much we have in the can. I don't need to calculate anything at all. I know it is starting with 20 centimeters. When t equals 1, that means I'm going to use my handy calculator. And let's start plugging some values in here. We know it's 20 times 1/3 raised up to the first power. And so the height in the can equals 6.66 repeating forever and always. Now when our time equals 2, I could either take this value and multiply it by another 1/3, or I could type in that equation again, and I like typing in my equation, so it gives me a nice exact value every time. I don't have to worry about rounding. Height equals 2.22 repeating. And last but not least, when our time equals 3, ooh, 0.741-ish if we're doing a decimal. Now, there is a nifty button that turns a fraction into a decimal or a decimal into a fraction. I'm going to use that button on my calculator. It's second, this one right here. So I'm going to hit that second this to turn my answer from a decimal into a fraction. And it's telling me it's 20 over 27. So if you wrote these in decimal or in fractional form, that would be A-OK as well. All right, so that 2.222222 turned into a fraction. Oh, well, it didn't like that one. But we could turn any of our values into fractions if needed. It says to find f of 4 and see what f of 4 represents. Okay, well, t equals 4. Let's use that same equation. .247-ish, or as a fraction, 20 over 81. And what that represents, let's see, if our input, I'm thinking about it this way, our input is 4, so that means 4 minutes. Our input is time. So at 4 minutes, the output, the height of water, is 20 over 81, or 0.247 centimeters. So I'm going to write a sentence that says that. After 4 minutes, sorry, I kind of ran out of room here. The height of the water is 0.247 centimeters, or 20 over 81 if you want to be nice and exact. Nice. All right. So number 1, A through D is done. Let's flip on over and see what question 6 is asking us about. The graph shows an exponential relationship between x and y. We can see that nice curve happening. Write an equation representing this relationship. Okay. To write my equation, we talked about the starting times what it keeps from one step to the next, raised up to an x or a t value. This one, the starting is our y-intercept. My lines are going up by 50, so it tells us it starts at 50 right here. So there's how I'm going to start my equation. And I need to figure out what multiplier we're using. So 50 times something gets to 100. Or we could also look at 100 times something gets to 200. And you might be noticing that pattern is that it's doubling. So it's multiplying by 2 every single time. So part B says, what is the value of y when x equals -1? Label that point on the graph. Here's our point at -1. I know that first is our input, so I'm going to label it right under here. -1, comma. And let's see what kind of pattern. We mentioned as it's going to the right, it is doubling, so times 2 times 2. But if we're moving to the left, in order for us to find a negative exponent, looks like we're dividing by 2. So 200 cut in half is 100. Half of 100 is 50. Half of 50 would be 25. And to find our value when x is -2, looks like we need to move backwards one more time. And we need to cut 25 in half. So we're going to do 25 divided by 2, which is 12.5. And that's what our value would be here. So there we go.